Hello and welcome to this brief tutorial on the science behind the weekly crop ET reports. I am Alan Fulton, Irrigation and Water Resources Advisor for the University of California Cooperative Extension. I work in the northern Sacramento Valley in the counties of Tehama, Glenn, Colusa, and Shasta. Like rainfall, crop ET is reported in inches, or if we're in an area that uses the metric system, millimeters. The picture to the left shows a simplified idea of how crop evapotranspiration occurs. You see a prune orchard with young trees in a row. You see the shadow below them, and in that shadow is a single line of drip. In between the tree rows is the orchard middles that can have various types and amounts of vegetation. Despite this complex nature of the orchard, crop evapotranspiration is viewed as coming off the entire surface of the orchard. And for this reason, ET is reported as a depth like inches, very similar to rainfall. ET is water or moisture leaving the field instead of incoming. It's often unspoken, but the measurement area is an acre, or in areas that use the metric system, a hectare. The complete unit of measurement is inches per acre or millimeters per hectare, but to keep it simple, we just speak in terms of depth, inch or millimeter. The time step can range from hourly, daily, weekly, monthly, or annually, depending upon your needs. For irrigation management, a weekly time step or even more frequent is the most useful and beneficial. Real-time crop ET can be measured. We do this in research often. The oldest and most standard method of measuring crop ET is using a weighing lysimeter. It has been used worldwide. The picture on the left shows a weighing lysimeter being installed into the ground. It's essentially a planting box. You see the holes on the side to provide drainage and aeration. The box is placed into the ground and filled with the same soil as the surrounding field. And then the crop is planted inside this box to simulate the crop planting around it. The picture on the right shows an almond tree in a weighing lysimeter. You can see the wetted pattern below the tree. You can see the drip hose going lengthwise across the lysimeter. The actual crop ET is determined by measuring the mass or weight loss in the lysimeter on an hourly and then totaled for a daily basis. An alternative to a weighing lysimeter is a newer technique. It's a thermodynamic method referred to as the residual energy balance method for measuring crop ET. With this method, we use weather instrumentation. One of the instruments that we use is a net radiometer. It measures the incoming sunlight. It is a net radiometer in the sense that it measures all the light coming into the orchard, but it has the ability to measure the light that was reflected off the orchard floor and orchard canopy and on the bottom side of the sensor, so it gives us a sense of the net radiation. These two sensors over here measure wind speed and air temperature. This is a sonic anemometer. This is a thin wire thermocouple. It's very hard to see in this picture. These two instruments take measurements at a very high frequency, one measurement at 1/10 of a second. It's measuring the effect of the wind moving warm or cool air in and out of the orchard in a very dynamic fashion. It is measuring the H term in the residual energy balance curve. It's measuring the sensible heat that we feel. You cannot see it in this picture, but we have sensors buried just below the soil surface at a depth of about 2 inches. These sensors are measuring the heat flux. In the heat of the day, the soil absorbs heat. At nighttime, when it's cool, the soil releases heat. This is the G term in the residual balance equation. We take this information measured from these instruments, and we can then calculate a latent heat of evaporation. This is the residual energy left in the orchard to convert water to water vapor, which is essentially what we are doing with evaporation and transpiration, or ET. Measuring actual crop ET is getting easier and more affordable, but is not done at the farm level by most growers. In California, we see this done most widely in wine grape at the moment. As a result, we offer these weekly crop ET reports, and these reports are developed based on the information from the California Irrigation Management Information Weather Network. There are 150 weather stations in California. They report hourly ET for short grass reference conditions. In the Sacramento Valley, we have 8 CIMAS weather stations. This is an example of the CIMAS weather station located in Tama County. It is the Gerber weather station number 222. And again, we use the weather data and predictive models to estimate the hourly evapotranspiration for this short grass irrigated condition. And we accumulate the 24 hourly measurements to get a daily rate. What does short grass reference ETO tell us and not tell us? It provides a real-time direct measure of crop water use for irrigated pasture. It's a standardized measure of the evaporative demand for specific farming regions. It provides us seasonal changes in evaporative demand from the spring to the summer, through the fall, and even in the winter. And it gives us a sense of how normal or unusual the recent weather has been and how it affects evaporative demand. It does not give us precise estimates of crop water use for all the other crops that we grow in our farming regions. Nor does it give us a sense of evapotranspiration rates in unique microclimates. In fact, these weather stations are placed with the idea of representing the largest area possible. So in order to provide these weekly ET estimates for specific crops that we grow, we have to multiply the grass reference ETO by research-based crop coefficients, abbreviated by K sub C. These crop coefficients, as I've pointed out, are developed by various research methods. By definition, a crop coefficient is just the ratio of the actual ET measured in a field divided by the short grass reference ET measured at the nearest CIMAS weather station for the same period of time. If you have a question about what crop coefficient is being used in our weekly ET reports, you can easily calculate it. And I will show you in a later tutorial how this can be done. These are 3 tables showing the average monthly crop coefficient for 3 of the main crops we grow in the northern Sacramento Valley: almond, walnut, and prune. To the left, in the case of almond, you can see that we have crop coefficients for all 12 months of the year. Almonds are a longer season crop, typically blooming around the 15th of February. And during the spring months, you can see this crop coefficient increases as the canopy emerges and develops to its fullest shading capacity. In the summer, you can see the crop coefficient levels off and is at a maximum. And as the canopy gets older and ages, you'll see in the fall that the crop coefficient drops off. In a similar fashion, walnut does the same thing, only the crop coefficients are for a shorter period of time. Our major walnut varieties don't leaf out till the 1st of April, so we only provide crop coefficients in the spring months of April, May. You see they reach a peak high in June, July, and August, and they begin to fall off in September, October, and November as the canopy ages and gets closer to senescence. Prune is an intermediate crop in terms of length of season, not as long as almond, but longer than walnut. It's also a smaller statured tree. We tend to not have quite as much ground shading and light interception, and this is reflected in the crop coefficients. You see the lower crop coefficients in the spring, but you see that the maximum crop coefficients in June, July, and August are not nearly as high as the other crops, again, reflecting the shorter statured orchard crop. These are examples of crop coefficients that we use to provide you the weekly estimates of crop ET. Just to illustrate the point one more time, this is for walnut, 4 pictures showing how the crop coefficient corresponds with changing canopy. This is a springtime picture, April 21st in the year of 2011. You can see that there is grass cover in the orchard middles, pretty significant. The picture is not real good at showing it, but there is vegetative bud break and the canopy is emerging out. And this condition corresponded with a crop coefficient of about 0.74. Just 3 weeks later, the crop coefficient is increased to 0.96, and you can see that the crop canopy in this walnut orchard has changed drastically. A few weeks later, mid-June, the crop coefficient is reaching a maximum of about 1.04. And then in this picture, you can see an example for November. Crop coefficient has dropped way down to 0.6. You can see the aging leaves, the fall colors, and this corresponds with the lower crop coefficient. So this gives you some idea of the science behind these crop ET reports. Thank you for joining me.